set of isotopes is equal to the percent abundance for the first isotope times its individual atomic mass, plus the percent abundance for the second isotope times its individual atomic mass, etc. The calculation continues for all naturally occurring isotopes of the element. Remember that you calculate a percent as a part per hundred, so you'll use a fraction or decimal. This formula will not appear on a formula chart, but it is just a weighted average calculation. Your grade average for this chemistry course is also a weighted average calculation. Daily averages generally count for a smaller percentage, say 33% of the overall grade, than test averages, which might count for 67%. If you have a 90 daily average, but a 62 test average, what is your overall average for the course? It is not 76. To calculate your chemistry grade average, you would set the problem up this way. Daily grade percent, 33 divided by 100, times daily grade average, 90, plus test grade percent, 67 divided by 100, times test grade average, 62, which earns you a 71. Since the test average counts more heavily, the weighted overall average of 71 is closer to the test average of 62. Calculating your grade average is like having two grade isotopes that have a different weight or mass. Calculation of average atomic mass for a set of isotopes is as easy as calculating a grade average. It is a weighted average calculation.
Most people know that a couple is 2, a dozen is 12, a ream of paper has 500 sheets, and a grand is 1,000. How many is a mole? Scientists are often concerned with the number of atoms, molecules, ions, or formula units present in a substance. It is difficult to count the number of these representative particles because they are so small in size. Even a relatively small amount of a substance is composed of incredibly large numbers of these tiny particles. For example, a grain of table salt that has a mass of 0.01 milligrams contains over 103 quadrillion formula units of sodium chloride. Scientists address the difficulty in counting the number of representative particles by assigning a unit, called the mole, to represent a specific quantity of these particles. So the mole is the SI unit used to measure the amount of a substance. A mole of anything is equal to 6.02 times 10 to the 23rd. This number, 6.02 times 10 to the 23rd, is called Avogadro's number, in honor of 19th century Italian physicist Amedeo Avogadro. A mole is similar to other words that represent a specific quantity. Just as the word dozen can indicate 12 of anything, such as donuts, eggs, or roses, a mole could represent 6.02 times 10 to the 23rd of anything, including donuts, eggs, and roses. However, the mole is used in chemistry to represent 6.02 times 10 to the 23rd of tiny particles, such as molecules or atoms. Just as the mass in grams of a dozen donuts is different from the mass of a dozen eggs, the mass of a mole of water is different from the mass of a mole of salt. In order to calculate the mass in grams of 1 mole of any substance, scientists use the carbon-12 atom, considered pure carbon, as the standard for all mole calculations. The mole is more specifically defined as the number of atoms that are present in exactly 12 grams of carbon-12. In other words, 6.02 times 10 to the 23rd atoms of carbon-12 have a mass of exactly 12 grams. Scientists can use this definition of the mole to find moles of any substance. In order to calculate the mass in grams of 1 mole of any substance, a scientist could begin by calculating the mass of a single atom of carbon-12. Looking for grams per atom, she could divide the mass in grams for carbon-12 by 6.02 times 10 to the 23rd atoms. This gives 1.993 times 10 to the negative 23rd grams per atom of carbon-12. Once grams per atom of carbon-12 are figured, she could compare any atom to an atom of carbon-12. Recall that the size of atoms can be compared in terms of atomic mass units, or AMU. Carbon-12 has an atomic mass of 12 AMU. Hydrogen-1 has an atomic mass of 1 AMU. So hydrogen has 1/12 the mass of carbon-12. If hydrogen has 1/12 the mass of carbon-12, then the mass of carbon-12 can be multiplied by 1/12 to get the mass of hydrogen-1. The mass of hydrogen-1 is therefore 1.66 times 10 to the negative 24 grams per atom. By definition, a mole of any substance is the amount 6.02 times 10 to the 23rd. To calculate the mass of a mole of hydrogen-1, the mass of one hydrogen-1 atom, 1.66 times 10 to the negative 24 grams per atom, can be multiplied by 6.02 times 10 to the 23rd atoms per mole. The mass of 1 mole of hydrogen-1 is 1.00 grams. You would see this reported as a molar mass of 1.00 grams per mole. Notice that the molar mass of hydrogen-1 is numerically equal to the atomic mass of one atom of hydrogen-1. This numeric equality is no coincidence, and can be applied to an atom of any element on the periodic table. The mass in grams of 1 mole of any element is numerically equal to the atomic mass of that element. Remember that most elements in nature have isotopes with different atomic masses. The atomic mass you see on the periodic table is the weighted average of the masses of these isotopes based on their relative amounts in nature. This is why most elements on the periodic table have an atomic mass with a decimal value. The atomic mass reported on the periodic table for carbon is 12.011. This atomic mass is numerically equal to the molar mass for carbon. It can therefore be said that the molar mass of carbon is 12.011 grams per mole, or that 6.02 times 10 to the 23rd atoms of natural carbon have a mass of 12.011 grams. The atomic mass for gold is 196.97 atomic mass units. So 1 mole of gold, or Avogadro's number of atoms of gold, has a molar mass of 196.97 grams per mole. You can use the periodic table to find the mass in grams of 1 mole of any atom, because its molar mass is numerically equal to its atomic mass. The mole concept can also be used for chemical compounds. To figure out how many grams are in 3 moles of sodium chloride, you must first know that the formula unit for sodium chloride is NaCl. Next, add the individual atomic masses for all of the atoms in the formula. The atomic mass for sodium is 22.99, and the atomic mass for chlorine is 35.45. The sum of the two atomic masses is 58.44, so the molar mass for sodium chloride is 58.44 grams per mole. To find the mass of 3 moles of sodium chloride, multiply the 3 moles by the molar mass. Sodium chloride has a molar mass of 58.44 grams per mole, so 3 moles have a mass of 175.32 grams. In the same way, the molar mass of ethanol is the sum of the molar masses of all the atoms in the molecule. This requires multiplying the molar mass of carbon times 2, the mass of hydrogen times 6, and the mass of oxygen times 1. Then add the numbers for each of these to get the molar mass of ethanol, which is 46.069 grams per mole. In other lessons, you will learn how the mole concept is useful in solutions. A 1 molar solution contains 1 mole of a substance dissolved in a liquid to a total volume of 1 liter.
Okay, and let's go to the last one, molar calculations.
Why do many chemistry classes celebrate October 23rd as Mole Day? One mole of a substance is the amount 6.02 times 10 to the 23rd, which is Avogadro's number. This is the number of carbon atoms in 12 grams of pure carbon-12. The mole concept can be used to determine the numbers of atoms, molecules, or formula units in any amount of a substance if the molar mass of the substance is known. Molar mass is the mass in grams of 1 mole of any pure substance. The molar mass of an element is numerically equal to the element's atomic mass, which can be found on the periodic table. For example, the atomic mass of aluminum is 26.982 AMU. Therefore, 1 mole of aluminum will have a molar mass of 26.982 grams per mole. A mole contains Avogadro's number of atoms, so 26.982 grams of aluminum contain 6.02 times 10 to the 23rd aluminum atoms. When calculating in chemistry, it is necessary to use moles to convert from mass in grams to number of representative particles. This is because mass and number do not have a direct correlation on the atomic level. 10 grams of salt and 10 grams of sugar do not have the same number of molecules. A mole map like this one shows all of the possible mole calculations for converting between mass and representative particles. Notice that no matter whether we begin with grams, mass, or atoms, representative particles, we always find moles before completing the calculation. To use the mole map, follow the arrow and stay on the right side of the road. Remember that the molar mass of a compound can be determined by adding the atomic masses for each of the atoms in the molecule. For example, copper 2 sulfate is CuSO4. Each formula unit of CuSO4 has 1 copper atom, 1 sulfur atom, and 4 oxygen atoms. Adding the atomic masses of the 6 atoms gives the mass of the formula unit. Therefore, 1 mole of CuSO4 has a mass of 159.608 grams. Suppose you have a 1.25 gram sample of copper 2 sulfate. How many moles is this sample? Following the arrow, the mole map shows how to get from grams to moles. First, write the mass of your sample, and then divide it by the molar mass of CuSO4 to get the number of moles in your sample. 1.25 grams of CuSO4 is 0.00783 moles of CuSO4. Now that you know the number of moles in a 1.25 gram sample of copper 2 sulfate, you can also determine the number of formula units in the sample. Multiply the number of moles in the sample by Avogadro's number to get the number of formula units. There are 4.71 times 10 to the 21st copper 2 sulfate formula units in a 1.25 gram sample. A mole map also indicates calculations for converting both mass and representative particles to volume of a gas at STP and vice versa. You will learn how to use this part of the mole map in lessons on gas stoichiometry.
Okay, so that's the end of it. Please make sure you answer the questions that go along with it. Get it turned in on time. We will go through our notes, and I will also video our notes to kind of help us out. Again, a lot of this is going to be the dimensional analysis that we learned last unit, and we needed to practice dimensional analysis so that way we can get better when we started on this unit, okay? Well, thank you for everything. Y'all have a good day. Bye-bye.